Right, number 15 then, 5 marks. From paper 2 of the 2025 Advanced Higher Maths, it's this proof by induction. It's got fractions in it. So now immediately I'm going to run out of space here. Proof by induction that for all positive integers n, so n is a member of the positive integers, 1, 2, 3, 4, 5 in other words, whole numbers, that this proposition, this is true. So that's the proposition. You can call it proposition if you like. Well, let's test it first of all, at the very first one, so that's 1. So let's test it for n equals 1. If n equals 1, what have you got? You've got from 1 to 1 of this, so it's just the first term. So it's going to be 1 over, put down the working, 2 times 1 plus 1, times 2 times 1 minus 1. So that's 2 and 1 is 3 times 1, so that's a third. The other side, maybe I should have called it that, right hand side now, will just be 1 over 2 times 1 plus 1, which equals a third. So I'll just change that to right hand side equals. Which means that that proposition is true for n equals 1. Now I don't know where I'm going to put all this. Right, so now the inductive hypothesis. Now we're going to assume. Let's just assume it's true. Assume that P is true for some random number, n equals k. If that was the case, that means that if you were to do sigma r equals 1 to k of 1 over 2r plus 1 times 2r minus 1, the answer should be k over 2k plus 1. K being the number at the top, k being the number here that you put in. Right, so that's the inductive hypothesis. Now we're going to consider this. What about n equals k plus 1? What would happen for that if that were true? Well, r equals, we could run out of space. If I was to go as far as k plus 1 of that same expression, 2r plus 1, 2r minus 1, I'm not going to put that in obviously, that would be equal to the previous one, because that's just a sum of terms, that would be equal to the sum of, so much writing in this part, which is 2r plus 1, 2r minus 1, and obviously that's going to be the sum of the first k terms plus one more term, the last term that took you up to k plus 1. So the last term that took you up to k plus 1 would have been this inside term here, the last one would have said 2 times k plus 1 and 2 times k plus 1 minus 1. Not got much room. Now what we can do is this, just do it here will I. Now this part here, I can call in 1 by 1. I'm saying that this part is equal to k over 2k plus 1. And onto that I'm going to add this lot. I'll just tidy that up. That's 2k plus 3. And that's 2k plus 2 minus 1 is 2k plus 1. I'm going to run out of room. Now we just need to add this together and hopefully end up with that expression, only with k plus 1s instead of k, or if you like here with k plus 1s instead of n's. Right, you can always shift, I'll just have to shift it up. Well, I've got a common factor there, so all I need for the denominator is 2k plus 3 times 2k plus 1. So I've got that already here, that's one of them, but this will need multiplied by this. So I've got k times 2k plus 3 plus 1. And now we need to shift it to get more space. So moving that up here, just to get the space, we've now reached that point here where, considering k plus 1, you would have this expression if that part were true. Now if I can make that look like this for k plus 1, then that's it. Well, let's just multiply that out. 2k squared plus 3k plus 1. Always happens when you've got these fractions, it just takes up twice as much space. Now factorise the top, and hopefully it will knock out one of the factors underneath, or else you have to go back through everything and check for a mistake. So that'll have to be 2k times k, that'd have to be 1 times 1, and that's perfect for 1s. They disappear, so I'm left with k plus 1 over 2k plus 3, and I can rewrite that 2k plus 3 as 2 lots of k plus 1 plus 1. And that's the required result. That's the result for n being replaced by k plus 1. So that equals the required result. The required result for n equals k plus 1. They just make the final statement. So what that tells you is, I should be really writing it down here, is this. What this says is, if p is true for n equals k, that means that p is true for n equals k plus 1. That's what that's told you, because you assumed it was true for that. If it was true, then it's true. It works for this one. But since p, just give it a name, is true for n equals 1, that means by the inductive step, because if it's true for 1, it's true for 2, and if it's true for 2, it's true for 3. That means p, or maybe we should say by induction, then by induction, or maybe I should say by mathematical induction, by induction, p is true for all n, where n is that.